Hi, everyone. In this video, I will be giving a demonstration of how to test a first stage moderated mediation model using the process macro with SPSS. So basically, the first stage moderated mediation model is associated with process template number 7. And as you can see on your screen right here, I actually have a couple of examples. The first one is more of the conceptual model, and the second one is the example that we will be using as we analyze our data. So before I get started, I do want to mention that underneath the video description, you'll find a link to the SPSS data file that I'll be working from in this presentation, so you can download a copy of the data to follow along. You will also find a link to a PowerPoint that's going to provide a lot of additional details that you might find useful as you're learning about this particular topic. So before we actually open up SPSS and begin running analyses and so forth, let's just begin with a little bit of a background. So you'll notice on this particular screen right here, I've got, again, the two conceptual models, basically. The first model at the top, this is just a standard mediation model where we have three variables. We have X, M, and Y. And so basically, the X variable is our independent variable within the model. The M is the proposed mediator, and then Y is the dependent variable within the model. And by the way, it would be possible to generalize this further on out and have multiple mediators, but we're just sticking with the most simplified example as we go through this discussion. So in this particular case, you'll see that we have three paths. Essentially, the single-headed arrows are paths in our model. And we have path A, we have path B, and then we have path C prime. And those paths basically represent direct effects of one variable on another variable, or the direct effect of one variable on another variable. So path A, the regression slope, represents the direct effect of the independent variable X on the proposed mediator M. Path B represents the direct effect of the mediator on the dependent variable. And then path C prime represents the direct effect of X on Y. Okay, so this is the standard mediation model. And again, A, B, and C prime are all proposed direct effects within this particular model. Now, we can also talk about the effect of X on Y, not only as direct in the form of this C prime path right here, but also as indirect. And that indirect effect is quantified as a product of paths A and B. So if we compute the indirect effect and then test it for significance, and we find that the indirect effect is significant, then we basically conclude that indirect effect is consistent with what we would expect for a model where M is mediating the effect of X on Y. Doesn't mean that we've proven mediation, but the outcome of our statistical analysis would be consistent with what we would expect if M is doing any type of mediation. Now, the model below is just kind of a modification of the model that you see above. And in this model, we are adding this variable W right here. And you'll see that we have an arrow that's pointed from W to the arrow that points from X to M. And what this is reflecting is the idea that the path from X to M is not unconditional, but rather the regression slope varies as a function of the proposed moderator. So in other words, the effect of X on M it varies depending on what level of W that we are observing. So that's that idea is reflected right here with A given, that's our vertical line right there, given W is equal to some value of W. So when we talk about the effect of X on M at a given value of W, what we are referring to is a conditional direct effect of the independent variable on the proposed mediator. Now, when we look at the path B and path C prime, both of these are unconditional effects, and that's because basically we don't have any kind of conditioning variable associated with each of those paths. So the effect of M on Y doesn't vary across any levels of any other proposed moderating variable. So path B is a constant, and path C prime is also constant because it's reflecting an unconditional effect of X on Y. Now, in terms of the indirect effect, we can compute a conditional indirect effect as path A given the moderator is equal to some value multiplied by path B. So that actually gives us an indirect effect that is conditional on W. So in other words, when we talk about the indirect effect within this model, we're not talking about A times B in terms of just a single value, but rather the value of A times B varies depending on levels of the proposed moderator. And so in that case, then we talk about the indirect effect as being conditional on the value of W. Now, we can kind of break down that conceptual model into a statistical model and just kind of further think about what all this means. On the left, we have actually two submodels. We have a regression model where the proposed mediator is regressed onto variable X, our independent variable, W, the proposed moderator, and the product of X and W. So in terms of the regression slopes here, we have A1, A2, and A3, where A3 is the regression slope for the interaction term. Okay, so when we look at the prediction model for the mediator, we have the predicted value on the mediator is equal to the intercept plus the regression slope for A1 times X plus the product of A2 times W plus the product of A3 times the interaction term X times W right there. So when we talk about the conditional direct effect of X on M, we can denote it right here with a theta subscripted X arrow to M. That is equal to A1 plus A3 times W right there. So that's basically the first model that we're talking about. That's a kind of a submodel that's built into the overall model. The second submodel, we have Y regressed onto X and M. So you'll see right here that we have the regression slope C prime and B right there, and those would be computed over here as, for the B and C prime paths in our conceptual model. So as you can see right here, then we've got the predicted value on Y is equal to the intercept plus the product of X and C prime plus the regression slope for the mediator times the value of the mediator. So in a nutshell, we can use these two regression slopes to compute conditional indirect effects. And so that's kind of represented over right here. So we have the conditional direct effect of X on M times the regression slope, which is denoted with our path B up there. And that's what produces the conditional indirect effect. So when we think about, let's just kind of take now a look at our data and the model that we're going to be testing using SPSS. So right here, this is just kind of a screenshot of some of the data in our data set. And our data is actually based on that associated with Howe et al.'s 2020 article, Chronotype and Psychological Distress Among Chinese Rural Population, a moderated mediation model of sleep quality and age. And I will say that in their analysis, they actually use Hayes process model number 59. We're going to be using process model number 7. You could just kind of think about number 7 as being subsumed under model 59. So in terms of our variables in this particular model, and this is just a conceptual model that we're testing right here, you'll see that we've got age, morningness, sleep quality, and psychological distress as our variables. And I've kind of changed the names of some of the variables and kind of altered a little bit about how things are presented right here, just to make it hopefully a little bit more intuitive. I personally don't do research on this topic of morningness, so I'm kind of doing the best I can in terms of interpreting relative to my understanding about what this actually means. But basically with the morningness variable, individuals who score higher on this variable experience greater alertness and performance during earlier morning hours and tend to prefer activities during daytime. Sleep quality, basically the original variable was scored such that higher values on that variable reflected lower levels of sleep quality. But what I ended up doing is transforming that original variable so that higher values on this particular variable represent greater levels of sleep quality. And then we also have our variable psychological distress, where higher levels represent greater levels of distress. So as we're looking at our model, you can see that we're basically postulating that the effect of morningness on sleep quality varies as a function of a person's age, and also that the indirect effect of morningness on psychological distress by way of the proposed mediator sleep quality is also moderated by age. I'll just also note that in the original article, the authors controlled for gender, family composition, etc. They basically included these variables as covariates in the analysis. We're going to keep things pretty simple in this particular demonstration, so we're not going to use the covariates option in process, but there is a box where we could include covariates if we wanted to. Just also showing you what process model number 59 looks like. You can see kind of down below, that's what model 59 looks like, and that's what the authors of that article actually had tested. So when we run our analysis using process, we're going to have two models that are going to be presented, and basically the results of these two models that will show up in our output. So in this particular model right here, the first submodel is one where we have morningness, age, and the interaction between morningness and age, all predicting sleep quality. So we have the regression slopes A1, A2, and A3 that are given there. And then for the second model, we have morningness and sleep quality as predictors of psychological distress. So that's where paths C prime and path and B are going to come from. So now what we're going to do is open up SPSS and run our analysis and go through the interpretation of our results. Okay, so here we have our data opened up, and so these are the variables that we will be using. This is the original sleep quality variable, but this is the transformation of it. That's the one we're going to use in our analysis. So we have morningness, psychological distress, age, and our transformation of that sleep quality variable. So what we're going to do is go to Analyze, go down to Regression, and then go down to Process. I've got 4.2 by Andrew Hayes right here. So I'm going to click on that. We'll move the distress variable to the Y variable box. We'll move morning to our X variable box. We'll move our sleep quality variable to the mediator box. And then we'll move age down to the moderator box. So just really quickly, though, before I do that, this right here, if I just, if I was to select model number 4, basically this would generate results for just a simple mediation model testing the effect of morningness on distress by way of the proposed mediator sleep quality. But instead, when I add in age as a proposed moderator and change this number to 7 right here, then at this point, we're going to be testing the model that we are proposing. Just so you know, too, you'll see that in terms of confidence intervals associated with the regression slopes and any bootstrap confidence intervals, they're all set at 95%. By default, in order to test the indirect effects, or basically the conditional indirect effects, and the index of moderated mediation, the process macro uses bootstrapping. So by default, it's set at 5,000. You can obviously change that number if you want to just by clicking this little arrow. You have a number of options for that. So next, what we'll do is we will go ahead and click on options. And so this box comes up right here. And I'm going to move myself over there a little bit. So in terms of our options, some of the typical ones that I'm going to select include generate code for visualizing interactions. Under mean centering of construction of products, I'm going to select only continuous variables that define products. And we're going to leave the probe interaction set at the default p less than 0.10 and conditioning value set at 16th, 50th, and 84th percentiles. So just briefly, in terms of what these options are doing, one of the things is that when you run your analysis, if our interaction term is statistically significant in the first submodel, basically the interaction between morningness and age, if that effect or that interaction is statistically significant, then we're going to want to probably probe that interaction to better describe what's going on. Okay, so in other words, better describe the nature of the change in the regression of sleep quality on morningness as a function of the moderator. So one way we can do that is to generate a plot of the simple slopes, or basically conditional effects, and to kind of describe what's going on. So if we click on this button right here, generate code for visualizing interactions, that's going to allow us to do that. Where it says mean center for construction of products, we selected this option right here. So oftentimes when people are running analyses involving moderation, mean centering is is very helpful. It's not required. A very common misconception in the context of moderated multiple regression is that it is a requirement that your X and your W variables be mean centered. That's not actually a requirement, but by mean centering, it does facilitate interpretation. And so that's why we're going to select that right here. If we had selected all variables that define products, by the way, this would have been fine as well, given that both age and morningness are both being treated as continuous variables. It's not going to make any difference. But where there might be some differences in terms of some of your output would be, let's say that either X or the W variable is a binary variable. Then in that particular case, if you selected all variables that define products, then even the binary variable would be mean centered before forming the product. So that's just kind of an FYI. If you decided, if you had a binary X or W variable and you selected that option, then you will get a mean centering for that variable. Whereas this option right here will only involve mean centering of those variables that are treated as continuous. So that's just kind of a FYI. In terms of down here where it says probe interactions, as I said up here when I was talking about generating the code, if the interaction is statistically significant, we oftentimes want to follow up by sort of exploring how those regression slopes, those conditional direct effects might vary as a function of the moderator. So if this is significant, one thing that we can generate are conditioning values, where we generate the simple slopes and then also associated tests of those simple slopes. And when I say simple slopes, I'm just kind of going back and forth, but meaning the same thing as conditional direct effect. So right here, the conditioning values are set for 16th, 50th, and 84th percentiles. Historically, folks have used this option right here of -1 standard deviation, the mean, and 1 standard deviation above the mean on the proposed moderator. But Hayes in his book really suggests using the conditioning values of the 16th, 50th, and 84th percentiles. This is just basically, this is more of an empirical basis for selecting those conditioning values, which is more useful in those contexts where you have non-normality for your moderator. In those cases where you would have normality of the moderator, then the results in terms of those simple the conditioning values and the simple effects and so forth will be more aligned between these two options. But we're just going to stick with the default right here of 16th, 50th, and 84th percentiles. So now let's go ahead and click also Johnson-Niemann output, and I'll talk a little bit about that in a bit. So we'll click on continue and then on OK. So it takes a second in order to generate our results. Okay, so here we are. And so we'll just kind of go through blow by blow different parts of our output. So you'll see up here, it's got just a description of the model. Model 7, Y is the distress variable, X is morning, M is our sleep quality variable, W is age, and then our sample size is 884. Just keep in mind that process uses listwise deletion when running the analysis. So we'll scroll down, and first thing that we have in our output is that first regression submodel. And this is just basically a least squares regression where we are regressing sleep quality onto morningness, age, and then the interaction between these two variables. Now, importantly, even though we have morning and age represented, because we had selected to mean center these variables, then basically these variables have been mean centered. And what that means is that for the morningness variable, we are essentially transforming that variable such that we just say morningness, I'll put a C right here for centered. That's just basically equal to morningness minus the mean for that variable right there. And then age centered is equal to age minus the mean for age right there. So those centered variables have a mean of 0. So this is going to be important when we're interpreting the regression slopes for these variables here. So first off, you'll notice that the model summary up at the top, we have the multiple correlation for the model. The R-square value is 0.0653. You'll notice that we've got the F value that's given, degrees of freedom due to the regression, degrees of freedom due to the residual, and then the P value. Unfortunately, there's a little bit of a misalignment in the labeling of these values, but so this is the P value right there. There's degrees of freedom, residual, regression right there, and F value. So just kind of pay attention to that. And there's a little bit of similar problems in terms of alignment down below. But as you can see, as a set, morningness, age, and their interaction jointly account for about 6.5% of the variation based on the R-square value in sleep quality. And you can see that they're jointly accounting for significant variation based on the results of our F test. When we look at the regression coefficients given by this first column, you'll see that we've got our regression slope for morningness, regression slope for age, and interaction down below right here. We have the standard errors that are given. Again, our alignment issues, you can see. We have the T values that are actually showing up over here in this column. The P values are showing up in this column over here. And then we have the lower and upper bounds for the confidence intervals showing up in these over here in these columns right here. So that's just kind of the way it's laid out, unfortunately. But anyway, in terms of the effects, the effect of morningness and age, now one of the things that folks oftentimes misunderstand is we're not interpreting these regression slopes in terms of in the same way that we might talk about effects in the context of an analysis of variance. These effects are not main effects, but rather they are conditional effects. Okay, so they're basically conditional direct effects. And what I mean by that is that the regression slopes for the variables that are comprising the interaction term basically represent the effect of a given variable on the dependent variable when the other variable is equal to 0. Okay, so in other words, when the other variable is 0. There you go. So what that translates then into is that, when age is equal to 0, the effect of morningness on sleep quality is 0.1223. Okay, and you can also see that that effect, if we look at the p-value that's given, is statistically significant. So we have a positive and significant effect of morningness on sleep quality for individuals whose age is 0. And just keep in mind that because the age variable and morningness variables, they're centered at 0, what that basically means is that for a person whose age falls at the mean in our sample, the effect of morningness on sleep quality is equal to 0.1223. If we look at the effect of age on sleep quality, right here, you can see that the effect of age on sleep quality for an individual falling at the mean on the morningness variable is equal to negative 0.0264. Now, in terms of that effect, you can see it's not statistically significant right there. So I'll put a little NS for non-significant. Then we have the interaction term, and we have the regression slope for it. And basically what this is representing is the change in the effect of the slope for morningness per unit increase on the age variable, our moderating variable. So you can see right here that the regression slope is negative. And what that basically means is that, if we start at the mean on age, the regression slope is 0.1223. And then for every unit increase on age, that regression slope is actually going to be decreasing by 0.005. You can also see right here that the interaction term is statistically significant. So what that's telling us is that the effect of morningness on sleep quality varies across levels of age. Now, because that effect is statistically significant, then that's where we want to kind of follow up and kind of probe that interaction, kind of explore what that interaction actually looks like. Now, as you kind of scroll down a little bit further, or kind of go down a little bit further, you'll also notice this piece of output right here. And this is basically a test of the interaction term as well. But what you'll see right here, the R-square change that's given right here, this is basically computing the R-square, the change in R-square between a model that contains the interaction term and a model that does not contain the interaction term. So if we remove the interaction term from our model above, the R-square would decrease by 0.0049. And you'll notice that we have a significance test. It's basically an F test right there, and there's our p-value. And this basically is just the same test as what we have up here for our interaction. So you could, theoretically, you could use either one of those to talk about the interaction as being significant or non-significant. But most of the time, you just want to report in the context of using the regression slope for that interaction term. So I'll go ahead and scroll down a little bit further. And now we have our conditional effects of the focal predictor on values of the moderator. Now keep in mind that we've mean-centered the age variable. So what that means is that you'll have values of on the centered age variable that are negative and values that are positive. Okay, so because the mean is equal to 0. So what we have right here is this first column, we have levels of the moderator, and we have basically, because of our selection of 16th, 50th, and 84th percentiles of the moderators, these are the values of age at those percentiles. Then we have the conditional direct effects of morningness on sleep quality at those different levels of age. So this is the conditional direct effect of morningness on sleep quality at the 16th percentile on age, at the 50th percentile on age, and also at the 84th percentile on age. You'll also see that we have significance tests for each of those conditional direct effects. And so the p values are actually given in this column. Again, we have an alignment issue right here, but these are the p values for each of those three conditional direct effects. And you can see all three of those are statistically significant. You also notice that all the values are positive right here for those conditional effects. So really the direct effect of morningness on sleep quality appears to be positive and significant at each of those three levels of the proposed moderator. Now, just keep in mind too, though, that the significance of these direct effects is not what's really elucidating anything with respect to the moderation effect that's taking place. So, all three of these could be non-significant. All three of those could be significant, or you could have significant and non-significant tests. That really has no bearing on the question of moderation. The issue of moderation really pertains to the variability in the slopes for the effect of morningness on sleep quality across levels of our age variable. So, in other words, as you're looking at this right here, you can see that the effect of morningness on age at the 16th percentile is 0.16. Or excuse me, the effect of morningness on sleep quality at the 16th percentile of age is 0.1554. Then when we move to the 50th percentile of age is 0.1256. So you can see that there's a decrease in the direct effect of morningness on sleep quality. Then when we move to the 84th percentile, we have yet another decrease down to 0.0810 for the direct effect of morningness on sleep quality. So you can see that there's variability in those direct effects. And that is what we would expect in those cases where we have potential moderation. If we did not see variability in those direct effects, and that would be more consistent with a situation where there would not be moderation that's taking place. So that's kind of the way to think about things when you're kind of probing these interactions. It's not the significance of the simple effects themselves that really inform us about whether there's moderation, but rather it's the variability in those slopes that inform us. And the formal test of that variability in those slopes is given by the test of the interaction term up here in our regression results. So we can kind of further build on this idea if we go down and look at our Johnson-Niemann significance regions. And you'll notice that we have our age variable right here. We have different levels of our centered age variable. So we have, again, negative values and positive values as we move throughout the range of that centered variable. And then we have the conditional direct effects given in this column. So you can see right here, just looking at those effects, we start at 0.2150. And as we move from lower levels of age to higher levels of age, you can see that those conditional direct effects are getting weaker. So like when we move to, let's say right here, negative 0.6787 on the centered age variable, the conditional direct effect is 0.1256. If we continue on throughout the range of the age variable, then when we get up to this point, 17.3213, the conditional direct effect is 0.0363. So you can see that the slope, even though it's positive throughout the range of the age variable, the slope for the effect of morningness on sleep quality is getting weaker. It's becoming more negative, or basically signaling a weaker positive relationship. So as we're looking at this, though, you can see that we have a column where we have p-values for each of those, the tests of each of those conditional effects. So it's basically this column right here, even though, again, we have that misalignment for the headers. And as you notice, down here, we have 0.05 for the simple effect, or the conditional direct effect right here of 0.0649, falling at 11.5528 on the age variable. If we move to this next level right here of 11.9213, the slope is still positive, but then we have a transition to a non-significant conditional direct effect. So as you can see then, basically in this part of our results, essentially ranging from 11.9213 to 17.3213 on our centered age variable, all of these results right here would be considered non-significant, whereas the results that showed above, all of those are statistically significant. So you can kind of use the Johnson-Niemann regions of significance as a way of sort of parsing out those transitions between significant and non-significant conditional direct effects. Next, we'll scroll down and you'll see that we've got this output right here that's got some syntax, and that's because we clicked on that option earlier. So basically, by default, process is not going to generate the a plot of simple slopes or conditional direct effects. Rather, what it's going to do is it's going to print this out when you make that selection, and then you have to basically go in and generate that output yourself. So to do that, I'll go ahead and actually show you before moving on to the next part of our discussion. So I'm going to double click in this area right here, and you'll notice that the output then kind of around the exterior, you'll see that we have some dotted lines. Okay, so that's kind of your giveaway right there that you can now enter into this output. And what we're going to do is we're going to find our syntax, and we're going to highlight all of this down, all the way down. You'll notice too, there is a period at the very end, so don't forget the period. So we're going to highlight that as well, and we're going to right click and click on copy. Next, I'm going to go to File, New, and click on Syntax. And I'm going to paste that syntax in. So, and again, don't forget the period at the very end. So in order to generate our plot, we can highlight all of this, click on the green arrow, and you'll see at the bottom right here, we have our plot. Now, right now, it's just giving you essentially the predicted value on the on our mediator at each combination of the 16th, 50th, and 84th percentiles for morningness and age. So you can't really see the slopes very well. So one thing that you can do is to double click inside this box. And if you go over to this little area right here, it says add fit line at subgroups, click on that. And there you go. Now we have our regression lines, and there's a equation for one of them. I'm going to actually click off of attach label to the line and click on apply right there. Just get rid of it. When I close and then close out right here, we'll go back to our output. And there you go. So you can see in terms of the slopes, we have our values of age at the 16th, the 50th, and the 84th percentiles. Okay, and so the light blue line is essentially our age at the low age, if you will. The red line represents kind of a medium or average level of age, and then you can see the blue line, or the kind of turquoise line, representing kind of a higher level with respect to age. So these are just 3 points along the range for the age variable. So just kind of keep that in mind. So the designation of low, average and high, it's kind of still relative, but this is just kind of giving you a general idea. So you can see then that the slope for morningness, the slope for the effect of morningness on sleep quality is most pronounced for those individuals who are low in age. It's less pronounced for individuals who are kind of in a midpoint or mid-range, if you will, and then for weakest for those people who are highest in age. So that just kind of gives you a general visualization of the effect of morningness, the conditional effect of morningness on sleep quality. So that's basically all there is to it with respect to generating the results using that syntax. If we scroll down a little bit further, you'll see that we've got the second regression submodels, where we've regressed distress, psychological distress, onto morningness and Sleep quality. So here's our R-square value for that model. It's 0.0527. So jointly, morningness and sleep quality account for about 5.3% of the variability in distress. You can see that with respect to the F-test, we have statistical significance. So as a set, the predictors are accounting for significant variation in distress. Because we don't have any kind of moderating variable for those remaining paths, these effects are essentially unconditional. So you can see we have a negative predictive relationship between morningness and psychological distress, and you can see it's statistically significant. With respect to the sleep quality variable, we have a negative and significant predictive relationship as well. So basically, individuals who are higher in morningness and also individuals who are higher in sleep quality, but those individuals tend to exhibit lower levels of distress or psychological distress. We'll scroll down next to the direct and indirect effects of exon Y. This right here, this first piece, is basically just a simple linear regression regressing our X variable, which is more, or regressing our our psychological distress variable, or Y variable, onto X, which is morningness. So this is just a regression slope, and then we also, you can see we have a significance test right there. So the zero order predictive relationship of X on Y, or morningness on distress, is negative and statistically significant. Next, we'll kind of scroll down a little bit more, and we'll start taking note of the conditional indirect effects. So as you can see right here, we've got indirect effect, morningness on distress by way of the proposed mediator, sleep quality. So in the next part of our output right here, we have the conditional indirect effects. It's basically the product of the A path given W and our B paths. Sorry, there's a lot to remember as we're going through all this stuff. So in a nutshell, at the 16th percentile for age, the conditional indirect effect is negative 0.2681. At the 50th percentile of age, it's negative 0.2167. And then at the 84th percentile of age, the indirect effect is negative 0.1397. So these conditional indirect effects, they can all be tested out using the bootstrap confidence intervals that have been generated. So as you can see right here, we've got basically the lower bound of the 95% confidence intervals and the upper bound for those intervals. And the basic decision making is this, that if the conditional indirect effect is equal to 0, that means that the indirect effect is, 0. That's basically in a nutshell. So what we're testing is whether the indirect effect, the conditional indirect effect, is non-zero. So the null hypothesis is 0. And so what we're doing is we're essentially taking that value and determining whether 0 falls between the lower and the upper bound for a given conditional indirect effect. So if 0 falls outside the lower and the upper bound, then we would determine that the conditional indirect effect is non-zero. If 0 falls between the lower and the upper bound, then we would conclude that the indirect effect is equal to 0. So in other words, if 0 falls outside the lower and the upper bound, we kind of deem it as significant. If it falls between the lower and the upper bound, then we deem it as non-significant. So you can see with respect to the conditional indirect effect at the 16th percentile for age, 0 falls outside the lower and the upper bound for that particular confidence interval. So we would deem that as statistically significant. Then when we look at the 50th percentile, the lower and upper bounds range between, or that confidence interval ranges between negative 0.3149 and negative 0.1313. 0 obviously falls outside of that range. So in that particular case, the indirect effect would be statistically significant. And then finally, we see that we have the last confidence interval ranging from negative 0.2568 to negative 0.0356. So 0 again falls outside that interval. So we would deem that effect as statistically significant. As I mentioned earlier, though, we can't really look at these effects in and of themselves as evidence of the moderation taking place. The idea of the conditional indirect effect is that the indirect effect itself varies across levels of the moderator. So, what we would expect if there is evidence of moderation is for these values in this column right here to vary, to not be all the same. If they are all the same, then the indirect effect is not being moderated, or it would not be consistent with what we would expect if the indirect effect is being moderated by W. So at any rate, as you can see, as we move from lower age to higher age, the indirect effect basically becomes less pronounced. So you can see at low age, the indirect effect of morningness on distress is most pronounced. It's a pronounced negative value of negative 0.2681. Then as we move to the 50th percentile, that effect, the indirect effect becomes a little bit more positive. So it's still negative. The value itself is negative, but now we have a weaker negative relationship between morningness and distress. And then when we move to high age, or the 84th percentile of age, we have an even weaker negative relationship between morningness and psychological distress. So again, we have some evidence that there's some changes in the effect of morningness on distress, or the indirect effect of morningness on distress across levels of the moderating variable. But we can formally test that out using the index of moderation, or moderated mediation, which is presented right here in this next piece of the output. So the index that's given right here represents the change in the conditional indirect effects per unit increase on our proposed moderator, which is age. So we can test whether we have evidence of moderated mediation by using the bootstrap confidence interval that's presented right here. And we're using the same logic that we had used previously when we were talking about the test of those conditional indirect effects up here. So basically, if 0 falls outside of the lower and the upper bound of our bootstrap confidence interval down right here, then in that particular case, we would have evidence of moderated mediation. If 0 falls between the lower and the upper bound, then we would have evidence that the mediation is not being moderated. Now, in this particular case right here, you'll see that the bootstrap result gives us an interval that ranges between negative 0.0002 and 0.0190. Okay, so in that particular case, if I was just basing my my analysis or my interpretation on this result right here, then that would be an indication that that we do not have evidence of moderated mediation. But but one of the things to kind of keep in mind when you're running your analysis using the macro, the drop-down system with process is that the bootstrap results are based on utilize a random seed number. Okay, so in other words, what's going to happen is every time you run your analysis, like if you run the analysis like right now, and then you rerun the analysis, let's say 5 minutes from now, different seed numbers will be used in order to as part of the bootstrapping process. And so the values of the lower and the upper bound for those confidence intervals will tend to shift a little bit, not a whole lot, but it will tend to shift some. And so that can, sometimes be the difference between, finding significance and non-significance. Most of the time, it doesn't seem to have that much of an effect, but in this particular case, it kind of did, because in the PowerPoint that I put together just yesterday, that I was mentioning that you could download, we had evidence of moderated mediation, and it's just because there's such an ever so slight shift in those values. Now, that may be a little bit frustrating for folks. And I will mention that, unfortunately, there's no way to set a seed number so that, if you run your analysis today on your data and then you rerun the analysis tomorrow, um, you know, if you could set the seed number at a particular value, then you would get the same results in terms of those confidence intervals. And unfortunately, through the drop-down system, you don't have that option. If you use the syntax-based option, with process, then in that particular case, there is the option to utilize to specify a seed number so that you don't get sort of the changing results with respect to the bootstrap confidence intervals. Everything else, like I said, in terms of the normal theory tests and so forth, all those are going to be exactly the same. The problem that I'm identifying right here really pertains to the bootstrap confidence intervals. So just be aware of that when you're running your analysis.